Let's have a look at a couple of example problems where we're going to use the normal distribution. So let's just remind ourselves before we get going. You see that we've got 3 problems there. Let's remind ourselves what this is about. So I just want you to think of a function that we had a single mathematical variable function, y equals x squared. Remember those from school? So let's have a look at our function here. F of x equals ax squared. X is our mathematical variable, and it's a real number, so it goes all the way from negative to positive infinity. And a is a coefficient. You might remember from school that's a coefficient. It's just a constant. Every time I plug in a different value for a, I'm going to get a slightly different curve. And remember, we can plot these. These are very simply just lines or curves in the plane. And so what I've done with the code here, please ignore the code. This is not about learning how to code. But I can certainly execute this line of code. And there we go. We see our function. And I have the value a there, and as I change a, you can see my curve changes. So for every specific a, I get a different parabola. And that's what it's all about. The normal distribution is also a function. We see it's a function of x. It's right there, but I've written it in a slightly different way. Instead of that, just the single parameter a, we've got these 2 parameters, mu and sigma, and those would be population mean and population standard deviation. Because remember, this little x that we see here just represents a specific realization of the random variable x, which we usually, as you can see there, denote with an uppercase x. So unlike a mathematical variable, its cousin, the random variable, is not only the little x values, but they also have what I like to call a little bit of metadata attached to them. And that is, on any specific interval, you'd find a probability of finding x on that interval. Remember, we cannot calculate the probability that a random value takes on a specific value. That's undefined because, well, that's just really nothing. And so we have to think about little intervals. But there's my equation. You can see it there. It's fairly simple. If you break it down, you can see it's 1 over the square root of 2 pi times sigma. And then that e is Euler's number. It's a specific constant to the power negative x minus mu squared over 2 sigma squared. And we can just simply plot that. And I'm going to plot that on a little interval of -7 to 7. There you can see I've also just colored this area under the curve because that's what it's all about. And as I change mu, look what happens. If I make mu more negative, it goes to the left. I make mu more positive, it goes to the right. So this peak is always going to be right at mu. And look what happens. Let's just bring it back to the middle somewhere. Look what happens when I change sigma. If I make sigma larger, see it gets flatter. But the 2 tails, the left tail and the right tail, you can see more and more of the probability gets pushed into those tails, because remember, this y-axis is probability density. And if I make sigma less, the standard deviation less, there's less and less spread, and you can see it becomes more and more peaked, and we remove some of that probability out of the tails. That area under the curve gets removed. The thing here is, though, that this function is completely defined, this curve is completely defined by these 2 parameters. Just as I did ax squared, if I changed a, I get a different curve. Here I also get a different curve, but this time there's 2 constants, mu and sigma. So for every specific population mean and for every specific population standard deviation, I'm going to get a slightly different curve. The thing about the curve, though, it's a very special curve. All these probability density functions are such that the total area, which I've shaded for you here, is 1. And that is what is very special about these functions, these probability density functions. The area under the curve, between the curve and the horizontal axis, that area is always going to be 1. I want you to think of it as a geometric area, like the area of a rectangle or a triangle or a circle. This is a specific funny looking shape. And what's very special about it, if I use integral calculus, if I calculate this area under the curve, it's going to be 1. And what we want to relay here is that the probability that x takes on any value on this x-axis, so from negative infinity to positive infinity, over all of those possible values that x can take, if I just look at all of them, so any one of them occurring on this whole big interval is 100%. The value of x must fall somewhere on this interval from negative infinity to positive infinity, so this is a beautiful mathematical representation of the probability of finding a random variable on a certain interval. Now it does go from negative infinity to positive infinity. These lines as they go out, they get closer and closer and closer and closer to the zero value on the vertical axis. And with all of that, it really just means we can look at a little interval, calculate that area under the curve on that little interval, and that is like multiplying the base times the height for that sort of rectangle that you can form there. And that is always going to be some proportion of 1, some fraction of 1, and that's the probability of finding x on that interval. And so the normal distribution is just one of many distributions, and we can find this probability density function of that distribution, and we say, well, maybe something in life, in real life that we measure, follows this curve. In some intervals, you're more probable to find a value of x. And then out here in the tails, if we make little intervals here on the tails, it's improbable to find a value for x there. Now, these things are very simply just models of the real life. If we look at something that we can measure in real life, we've got to find its pattern. So on what intervals do you find values very commonly? On what intervals do you find them less commonly? And can you take one of these named distributions and all have different curves? They're not all nicely bell-shaped as the normal distribution. But you find the right distribution of this thing that you're measuring, and you can use that as a theoretical model of the distribution of that thing which you are measuring. And if that's a continuous random variable, remember, we usually give it the name uppercase X. Now, because there are infinitely many of these, there are infinitely many values of mu, because it's a real number. There's infinitely many values of sigma. So if you look at that, there's an infinite number, uncountable infinite number of these curves. So we really want to work with just a single one. And it's also very easy just to change it, any random variable x, in this instance from a normal distribution, I should say, to the z distribution or the standard normal distribution where the mean is 0 and the standard deviation is exactly 1. And you remember this little formula, which is quite easy. I take a value x, I subtract from it mu, and I divide by sigma. So if I'm using the normal distribution, I can just automatically convert it to the standard normal distribution by this formula, which is, as I say, quite easy to understand because any value x is going to be a certain distance from the mean. And I'm expressing that in units of standard deviation because I'm dividing by standard deviation. So let's have a look at the first problem. So researchers are interested in the levels of a specific hormone in the population. They use the symbol x to denote the hormone level as a random variable. Meaning if you walk up to someone, you measure that hormone, the value that pops out is random. And it is described by, or it follows a certain distribution. On some intervals, you're going to find many people with that hormone level, and on some other intervals, you're going to find less people. And so they consider the random variable to follow a normal distribution with a population mean of 25 and a population standard deviation of 3. And we write that in the notation, as you can see there, statistically, we would say x in this little tilde symbol. So x is described by the normal distribution on a mean of 25 and a variance. We usually write variance there. So we've got to square that standard deviation. So 3 squared. Now remember, this is a choice by the researchers. They believe that this is a good model to represent the pattern of values for this hormone that you would find in the population. That was a chosen thing. They think this is a good model. So let's just assume that this is so. They are correct. This is a good model. Let's have a look at their curve. There's their curve. I've got a mean at 25 and I've got a standard deviation of 3. That means, values around 25. If I make a little interval around 25 and I look at that total area under the curve, that's going to be a large proportion of 1 of the whole area under the curve. And that means there's a very high probability of finding a value around 25. If I create, say, from 23 to 28 on that interval, I'm going to be most probable to find a value there. And so it's quite easy to interpret a curve like this. So if this is indeed a good model for the distribution of the values of this hormone, they want to calculate the probability that a randomly selected person from the population has a hormone level at most 23. So you can state this in various ways. You can say, well, what proportion of the population will have a hormone level of 23 or less? Or you can state it as we've done in this problem. If I take a randomly selected person from this population, what is the probability that they fall on this interval from negative infinity all the way to 23? Now, remember, there's no ways that someone has a hormone level of negative 25,434, but this is a theoretical model of the distribution of these hormone levels. So let's write down, and we can see in 3 how we wrote down their question in statistical notation. We said this uppercase P stands for probability. What is the probability that this random variable X, or this hormone level, is less than 23? Now remember, we could have also have said less than or equal to 23. That makes no difference whatsoever. So let's just do a little bit of algebra from school. So there I still have the probability that X is less than 23. Now this is an inequality. Remember, we get less than, equal, or greater than. Still just a little expression that we have there. X is less than 23. What I do to the left-hand side, just as with an equation, I also have to do to the right-hand side. And that's all I do in this second line. I say, on the left-hand side, let me subtract mu. That means I must also subtract mu on the right-hand side. Now, mu happens to be 25. So on the right-hand side, I'm subtracting 25. On the left-hand side, I'm subtracting mu. I am not changing this inequality at all. I'm not changing the inequality at all. What I'm doing to the left-hand side, I'm doing to the right-hand side. Now, on both sides, I'm going to divide by sigma on this line. And so on the left, divide by sigma. On the right, I just plug in the value that I know for sigma. Now, is this sign going to flip? No, it doesn't flip because I'm dividing by a non-negative number. And by that, also remember, we cannot divide by 0. Now, this is not dividing by 0. It's not dividing by a negative number, so nothing happens to that sign. It's an illegal, I should say, inequality that I have here. I don't have to flip the sign. I'm dividing by a positive number. And now what I do realize is that here on the left-hand side of this inequality, X minus mu over sigma, I recognize that. That's nothing other than Z. So let me put Z there. And I do this simple little arithmetic on the right-hand side. 23 minus 25 is negative 2 over 3. So stating that question, what is the probability that X is less than 23, is exactly the same as saying what's the probability that Z is less than negative 2 over 3. Those are exactly the same thing. Now remember, X is described by the normal distribution on a mean of 25 and a variance of 3 squared. But Z is described by the normal distribution on a mean of 0 and a standard deviation or variance of 1. So those two things are differently described. They follow a different pattern. One is a normal distribution on those parameters. The other one's a normal distribution, the standard normal distribution. So let's plot these. And this is what we have when we just look at X. There is our probability density function from this normal distribution. And this is what we want to calculate. This area, the shaded blue area, this is the fraction of this total area under the curve, remember, which is 1, which represents the probability of being 23 or less. It's the shaded area from 23 all the way back to negative infinity. A better way to state that, it's actually from negative infinity all the way to 23. I always want you to create this little, even if you just take pen and paper, just draw that line, shade it in, and you know exactly what is being, what this problem is all about. Now look at this. I'm just going to plot it as the Z distribution, and you can see there, this is what that would look like. Now for this curve, this blue section is also less than negative 2/3. So negative infinity all the way to negative 2 over 3. So these two things are exactly the same. But look at the beauty of this. We're saying this is the pattern of values that we would find for Z, or in this instance for X. On some interval, it's very probable to find values. And on some, it will be less. And that's what this curve is trying to tell us. Over all possible values, the probability is 100% that X would be somewhere on negative infinity to positive infinity. But if I constrain myself from negative infinity all the way to 23, that's going to be the probability that X, that I find this hormone value at most 23. So 23 or less. Or I can also just do it in this Z. Now that's where you can get. If you take a course and you have to do this with pen and paper, this is as far as you can get. Now we have to use software, a computer language, Microsoft Excel, any kind of program or calculator that can actually do this calculation for us. So right down here, I've just used this language. This is the Wolfram language. You don't have to worry about that. I can just write the code and you can see it's 0.252493. So it's about 25%. This area under the curve is 25%. If I use the Z distribution, I'm going to get exactly the same result. So let's take a calculator that we can all use free of charge. And that is this NumWorks calculator. So you can just go to numworks.com and hit this emulator button. You can, of course, buy this calculator. I have not done so. I'm just using this free version online. And so what we want to do with this calculator, we see there's lots of stuff that this scientific calculator can do. I'm just going to press this down arrow until I get to, one more time, to distributions is what I want. So let's click on OK. I'm going to scroll down because I want to use the normal distribution. I'm going to click OK. And now I have a choice. Do I put in 25 and 3 or do I put in 0 and 1? So am I going to use the normal distribution as given in this problem, or am I going to use the standard normal distribution? Well, we've made all the effort of calculating the Z value, so let's go for the standard normal distribution. A mean of 0 and a standard deviation of 1. So let me click on all the way down to next, then click OK. And now I can plug in that value. Now I do want to show you, if I go here to the little left button and I get to this little graphic there and I click OK, it can actually do quite a few things for me automatically. Now I have got this left side, and that's why it's so important for you to just take pencil and paper, pen and paper, and just draw that. So you know it's this little left-hand side that we are after, this lower tail. And it's going to put an X there. You know, don't be confused by that. That's not a problem whatsoever. It's just going to put X there instead of Z. You can ignore that. We have put in 0 and 1, so we are dealing with Z. It's a standard normal distribution. Now it says, what's the probability that, should actually say Z as I say, but X is less than. Now I've got to put in -2 divided by 3. So that's all I'm going to do. So I'm going to hit the -2 divided by 3. And I'm going to click on EXE for execute. And there we can see negative, or at least 0.252492. That's exactly the same as we got with the software. And it actually shows us a nice little representation of that, exactly as we had with the software. This proportion of the area under the curve from -2/3, or from negative infinity to -2/3, that area there is 25% of the whole, or 0.252. So I just want to go back here. Let's plug in 25. Now this calculator doesn't want variance, it wants the standard deviation. So let me plug in 3. Let me go down and hit OK. And now I'm just going to plug in that 23, because now I'm using this specific value for mu and value for sigma. So this is a normal distribution. And if I now execute that, again, I'm going to get 0.252492.5 and the exact same plot as we've seen before when we use software. So you can do either. Now we're going to use the standard normal distribution more in a course in statistics. So it's good practice just to convert to a Z value and then work with that. It's just good practice. But as you can see here, and with the software, it's not required. Today's software calculators, they can do it all. You don't have to convert to. That conversion to Z in this case really came from the fact that once there was no calculators, there was no software, there was no computers, there was no Microsoft Excel, etc. And you had to look at a table at the back of the book, and all those things were done on the Z distribution. So you had to convert from X to Z. Great, let's look at the next problem, which said this time the researchers want to calculate the probability that a randomly selected person from the population has a hormone level of at least 30. We could also say what proportion of the population has a hormone level of 30 or more, given that this specific normal distribution is a good theoretical model of the distribution of these hormone levels. So if we write that statistically, that will be the probability that this random variable is larger than 30. Now we do know a little bit about the calculus, the integral calculus of this problem. We are going to calculate from -infinity all the way up to a certain point. So we actually have to convert this into this. And we use the complement rule, because if you think about all the values that X can take, if we go 30 or more, or we go less than 30, that's a complete division of that number line in two distinct disjoint sets. There's no intersection between those two sets, so I can use the complement rule. So I can say the probability that x is more than 30 equals 1 minus the probability that x is less than 30. And that's what we always want to do. We're always working from negative infinity up to a certain point. So less than 30 goes from negative infinity all the way up to 30. If I calculate that area under the curve and I subtract that from 1, I'm going to be left with the area under the curve from 30 towards positive infinity. And now I do exactly what I had before, because I want to convert to z, and z is described by the normal distribution on a mean of 0 and a standard deviation of 1, or variance of 1, and that is the standard normal distribution. So there's my statistical form of the question. It's 1, what is the probability of x being less than 30, and I subtract that from 1. That will give me the probability that x is more than 30. So I look at my inequality inside again. What I do on the left-hand side of the inequality, I do to the right. So first I subtract mu from both sides. Then I divide both sides by mu. On the left-hand side, I use the symbols. And on the right-hand side, I use the actual values. I'm not changing the inequality at all. I recognize this as z, so I can just substitute z in there. And 30 minus 25 divided by 3 is 5/3, 5 over 3. Let's visualize that both in terms of our random variable, and that's what we have, the probability that x is 30 or more. And remember, that's totally disjoint from this 30 or less. Okay, so if I calculate this negative infinity to 30 and I subtract it from 1, then I'm left with this blue shaded area at the top. If I use 5 over 3 and the z, this is what that looks like. I still want to know this shape, this funny looking shape. I want to know what is its geometric area. That is the probability, because this is a probability density function. And if I use software, I'm going to get to about 4.78%, 4.779%. And if I use the actual 25 and 3 or 0 and 1, I get exactly the same result. So let's go to the calculator, just make sure we also get 0.047779. So let's go back. I'm going to use, let's start with the 25 and 3. Let's do that as far as x is concerned. We have not converted to the standard normal. And what I'll do with this calculator, I'm going to go to the left to my little icon there. I'm going to click OK, and I'm going to choose this upper tail. So I'm going to go down, down until I get to the upper tail. I'm going to say OK. And now you see that's swapped over. X is now larger than. So let me go there, and let's say the problem asked for 30. So I'm going to plug in 30, and I'm going to say execute. And look there, 0.04779, that tiny little proportion of the area under the curve. Let's just be sure. Let's go back. Let's make it 0 and 1. So now we're using the standard normal or the z distribution. I'm going to click on OK. I'm going to go left because I still want to go to the upper tail. It's an upper tail problem. I'm going to hit OK. And now I'm going to say 5 over 3. So 5 divided by 3. And that's going to give me exactly the same thing. 0.04779. We get exactly the same solution. Now here's our final problem. This time the researchers still think that this normal distribution on a mean of 25 and a standard deviation of 3 or variance of 3 squared is still a good mathematical model for the distribution of this hormone level. Now they want to know what's the probability that a randomly selected person from this population has a hormone level between 21 and 24. So that's how we can write it in statistical notation. This random variable is between 21 and 24. Now we do have to break that down. Now the software in a calculator does all this for you. You don't really have to worry about it, but we still need to think about what's happening conceptually, because behind the scenes there is actually some mathematics going on, and we're using integral calculus. And so we have to take this larger area, remember, from negative infinity up till 24, and then we subtract from that area from negative infinity to 21. And if I do that subtraction, I'm going to be left with the area between 21 and 24. And that's what we do in this step. So you can pause the video and just have a look at that. I've got it broken down into 2 sections. And again, for each of these 2 inequalities, what I do to the left-hand side, I do to the right-hand side. And in the end, that would be the same as the probability that z is less than negative 1/3 minus the probability that z is less than negative 4 over 3. Let's have a look at that. there is that interval that I'm looking at. So this funny shape, I mean, it's got three nice sides, so almost like a rectangle, but the top is funny, so there's no closed form, nice pi r squared formula for that. I have to use integral calculus. We don't do that here. We can just use software to calculate for us, but I want you to visually think of this every time you get a problem like this. There's my normal distribution on a mean of 25 and a standard deviation of 3, and I'm saying what is this area under the curve on this interval, because if I can calculate this area, that is going to give me the probability that the hormone level is between these two values, 21 and 24. And think about also what we did. First we calculated from negative infinity all the way to 24. Then we calculated negative infinity all the way to 21. And if you subtract the latter from the former, all you're left with is going to be this little area. So let's just do it in after we've converted to z. And as you can see there, the probability that z is between negative 4 over 3 and negative a third, it's the same. You're going to get the same value there. Let's do that in software. And we get about 27.8%. That is the probability that a randomly selected person will have a hormone level between those two values. So between 21 and 24. Let's go to our calculator. So let's go back. Let's do the 25 and 3. That's just easier to do, but I still want you to do that full derivation going from x to z. It makes good sense because later on we are just going to use, in the course in statistics, we'll use the z distribution over and over. So it's nice just to get into that. So I'm going to click on OK. And now if I go back, I'm going to click on OK because now I want that second icon there because I'm between two intervals. I'm going to hit OK. And now if I go to the right, it's between 21 and 24. And if I click on execute, I see, lo and behold, the same exact solution, 0.278. So 27.8% probability that a randomly selected person will have a hormone level between 21 and 24. But remember, this is all predicated on the fact that this model that we're using, this normal distribution, is a good representation of what the actual real hormone levels is out there in the population.